similar in magnitude. Oh, sorry. Okay, are similar in but opposite have opposite signs. So the pressure volume term can in fact really dominate what types of systems are going to be stable. And pressure is obviously important in planetary sciences as well, in earth sciences, planetary sciences, in extreme environments such as nuclear explosions. It can be employed to create new materials. For example, superconductors. Many of the elemental systems that we know become superconducting under pressure. And other materials can be made in the lab. Super hard materials, one example is diamond, that can be made under pressure. And what I will refer to are high energy density quantum materials, and I will hopefully talk a little bit about electrides. I will not talk so much about deep life or nuclear explosions or planetary sciences in this talk. Okay. So how do we predict these really strange materials? As I mentioned, we don't know. When we learn chemistry, we learn what we experience at 1 atmosphere, and also the databases that are out there have this information of what kind of structures are stable at 1 atmosphere. So we can't really use too much chemical intuition or information found in databases to predict what kind of structures are going to be stable under pressure and also what their chemical compositions might be. So to computationally try to determine what structures might be stable, oftentimes what is done is some sort of crystal structure prediction methods are employed. There are different flavors of them. My group uses evolutionary algorithms, and we've written the X-TLOPT algorithm for evolutionary structure prediction towards this end. So the idea of this evolutionary algorithm is you first make a number of structures. These structures then are locally optimized, oftentimes with density functional theory, but it could be with interatomic potentials if you have them, to some sort of a near stationary state, hopefully a local minimum. And then our program will go in and see which ones have the lowest enthalpy and assign a probability to them according to a probability that they be chosen as parents for the new generation of structures that is based upon their enthalpy, with the lowest enthalpy structures having the highest probability. And then new structures can be made either by taking 2 unit cells and cutting them somewhere and splicing them together to make a single unit cell. And the idea of procreation, where you have 2 parents that make a child structure. Or you could take a single type of unit cell and mutate it in some way, either by straining the cell, taking 2 atoms and swapping the atoms with one another, or sending a ripple through the cell. And by choosing the most stable structures as being the parents of the new generation, you hope that you'll have survival of the fittest in terms of, and therefore you choose the local geometry or the environment that gives you the lowest energy or enthalpy, thereby finding the most stable structure for that stoichiometry or the chemical composition and pressure that you've chosen. So as I mentioned, we've written X-TLOPT. It's available under various open source licenses. It can have it's cross-platform. It works with various queuing systems and along with a number of codes that perform first principles calculations for periodic systems and also interatomic potentials. And we have this graphical user interface. Here I would like to advertise a little review that we wrote. This code has been around for more than a decade now, and we've made a number of improvements to it. For example, it's been shown that in your first generation of structures, if they have space group symmetry, you are going to evolve to the global minimum much more quickly, typically, than if you just choose a completely random population of structures. We've also introduced ways to duplicate match, so to remove structures from your breeding pool that are duplicates to some user-specified amount. This is important for keeping diversity in your breeding population. And we found ways to, for example, evolve multiple unit cells at the same time, introducing supercell detection, primitive cell reduction, and also support for these types of single molecule type units. And tests have been performed to show that nowadays we're able to much more quickly find the global minimum of systems with 48, 50 atoms per unit cell and up to ternaries than we were 10 years ago. In some cases, we don't have 100% success rates, but still, for example, for the strontium titanate case with 50 atoms per formula unit cell, we still would need to do a lot of optimize a lot of structures to be ensured that we have found the global minimum, unless certain choices are chosen in how you set up the search. But it's much better than where we were, like I said, 10 years ago. Another thing that we have employed within XTLOPT is the idea of a multi-objective search. So in the multi-objective search, you don't want to optimize only a single objective, i.e. the energy or the enthalpy, but we would like to minimize or maximize, in some cases, multiple objectives. So in this case, we would have the probability here given by PI that a particular structure is chosen as a parent for the next generation of structures as being some sort of a weighted sum of two objectives. We've implemented this previously for the objectives being Vickers hardness, and here either energy or enthalpy, with this W being a weighting function that tells you how much to favor a particular objective. And we've interfaced this with the AFLOW method, which is a materials database that has about 4 million computations, DFT computations on materials. And a machine learning algorithm has been trained on this database to, for example, give you the shear moduli or the bulk moduli of materials. And if we know what the shear moduli is, then we can estimate the Vickers hardness via this formula that was derived by Tetter, who actually worked with Russ Hemley many years ago. And this was a formula that was derived by thinking about the geometry of the Vickers indenter. So if we use the computed Vickers hardness along with the enthalpy, we can hopefully maximize the hardness and minimize the enthalpy to find new super hard materials. So here, this is some work that we have done currently that we have been working on in order to further this multi-objective type of searching. Because oftentimes we don't only want to be focusing on this global minimum, but we might be interested in a local minimum that has either some sort of a desired geometrical feature, maybe because we have some experimental information, or because we know from chemistry that a particular geometric feature would be good for a particular property. So what we've done is to interface XTLOPT with PyMetGen that can be used to analyze what types of crystal structures are optimized via our DFT. And then according to some sort of user-defined criterion that looks either at this kind of localine crystalline order or at the symmetry, you can remove structures from their breeding pool or set their energies to be artificially high so that they will never be chosen as parents in the new generation. And I'll give you some examples of how this can be used. So in this example of metastable phase prediction, we just want to illustrate how it can be done. So we're thinking about different nitrogen type systems, because this kind of a polymeric nitrogen could be a high energy density material in the sense that if you have these bonds and then you break them and you form N2, which has an extremely strong bond, then you can give a lot of energy off. So that's where the high energy density material comes in. And if you do a normal X-TLOP search on, say, Xenon N8 at 50 GPa, you end up finding that this is the most stable structure, where you have a number of N2 molecules that are surrounding xenon. So this is the unconstrained search. This is the structure that'll come out of it. Now, there have been previous studies that have shown that this type of a system is metastable. So in it, you have xenon that is kind of put into this kind of a macrocycle type looking nitrogen ring type system. And if we induce constraints on our crystal structure search, where the yellow circles, these are 3-coordinate nitrogen atoms, and the nitrogen atoms that do not have circles around them are 2-coordinate. And we specify that the ratio of 3 to 2 coordinate nitrogens that we are keeping in our breeding pool, we end up finding that this structure comes out as being the most stable, as denoted here by the star, and it is definitely not quite as stable as this XEN8. So this is just an example of how you can use these geometric constraints to target this system in the crystal structure search. Another example that is very useful to me is because I work a lot with experimentalists that look at hydride type systems. And often when they do their X-ray diffraction, they're able to say something about the symmetry of the heavy element lattice, but they don't know where the hydrogen atoms go. So this is an example from a manuscript which made some sort of barium hydride systems under pressure. They figured out that it should be this p63 mmC barium H2 and also some I4 MMM symmetry BaH4 system, where the symmetry only corresponds to the positions of the barium atoms. And in this manuscript, it was already found that the most stable structure, if you just perform, in this case, it was an air structure search, is this CMCM-BAH4 phase. However, within it, the barium atoms do not correspond to what was seen in the experiment. And it was already proposed in this manuscript that this I4 MMM symmetry structure is most likely what was made. But now, if we carry out a crystal structure prediction search, where we remove we take our structures that are optimized, delete the hydrogen atoms from them, and then restrict the breeding pool to only those structures that where the barium lattice would be I4 MMM, and perform that crystal structure search, then indeed we definitely find that this is the most stable structure. And what's important is that it is approximately 300 MeV per atom above the ground state. And if you look just in the output file, it would be ranked as the 354th lowest enthalpy candidate. So you would pretty much never look at it to consider it. And so this kind of if you did an unconstrained search, so this kind of a constrained search is quite important in such a case where you might be making some sort of a metastable phase in experiment. Okay, so turning now to the high temperature superconductivity portion, I'd like to mention work that was done by Neil Ashcroft. Obviously, most of us here know that Neil really helped evolve this idea that if you were able to make hydrogen a metal by using chemistry, then you could lower the pressure required for metallization at the same time as keeping all of the very nice properties for superconductivity, including a large electron phonon coupling due to the fact that you don't have screening of the core electrons by any other electrons within hydrogen, having a large vibrational mass of the hydrogen atom due to its low light mass, and if you were to have a large density of states at the Fermi level. One can see by some of these this formula that can be employed to estimate superconducting critical temperature, or TC, in light element systems, why you would need a high vibrational frequency density of states at the Fermi level and a large electron phonon coupling. These are all correlated with a high TC. So there has been a lot of progress in this field. That was, I think, first really driven by computations involving work at first on very hypothetical materials such as silane, which is work that Rold was involved in. And then finally in 2015, there was this experimental synthesis of H3S, along with a theoretical prediction that such a compound should be stable under pressure. And the TC for this system was found to be about 200 Kelvin at 150 gigapascals. And what was, again, even more interesting from a theoretical perspective is that there was a number of clathrate cages that have been theoretically predicted, where the hydrogen atoms are four coordinate, involved in these highly multi-centered type bonds, and they form these types of clathrate cages with the metal atoms sandwiched with inside them. And these types of cages are often formed when you have some sort of an electropositive element, like an alkaline earth or a rare earth within them. Okay, so I wanted to mention typically what the workflows are that are used to generate what these crystal structures could be and what calculate the TC. So oftentimes what is done is people use their favorite crystal structure prediction method to find what the most stable structure is for a given chemical composition or for a given space. And there's assumptions that people put into this, what types of chemistries and what types of unit cells will be considered. The next thing that would happen is one plots what the enthalpy of formation is with respect to the mole fraction of hydrogen to generate these so-called convex hull plots, and any structure that lies on this convex hull is deemed to be thermodynamically stable and potentially synthesizable. But again, there are a lot of questions that go into this. You know, do we consider zero-point energy? Do we consider entropy? What about configurational entropy? What about Gibbs free energy? So these are human-based choices of what is considered in determining which structures to consider in the next step. And in the next step, one would say, well, I need to make some sort of decisions on what structures I calculate the TC for. And I can't do it for everything. So I need to define some sort of descriptors and use practicalities in mind. You don't want low symmetry structures. You can't compute TCs of huge unit cells. And so you might say, well, I'm going to limit myself to looking at a high density of states at the Fermi level or a high hydrogen density of states at the Fermi level, since this should probably enhance the TC. Then the next questions to use would be, well, which method do I use to calculate the TC? There are a variety of different approximations, with the most simple being what's implemented in quantum espresso. But even in that case, there is a semi-empirical parameter, mu star, which can be set between 0.1 and 0.13. And so one might discuss which values to employ. And then we might have isotropic versus anisotropic calculations for the superconducting gap. That becomes more computationally expensive, and therefore would only be done in case somebody thinks that it's really quite necessary. And questions about potentially anhermeticity or various proton classical versus quantum dynamics. So these are all the kinds of considerations that one takes into account when studying these things theoretically. And in my opinion, oftentimes the crystal structure prediction codes give the same types of results as long as the people that use them make the similar types of assumptions in going into them. The way that people have different results is when the assumptions made by the human beings are different. Okay, so here are some examples. As I've noted, with H3S is a nice high temperature superconductor. So now we need to go to increase the complexity of the systems that we study, and we're turning to ternaries. So one idea would be to dope something into the H3S, and an example could be phosphorus. And one reason why phosphorus might be beneficial is that it has a similar atomic radius as sulfur. It has a fewer valence electrons, so it can be used to help position the Fermi level with respect to any peaks in the densities of states that might be found there. Phosphorus and sulfur can both be hypervalent, so one would expect that similar types of structures might be stable. And just phosphorus can have octahedral coordination, as we do find that sulfur here is octahedrally coordinated. So we've performed crystal structure prediction searches on these types of systems. This is a typical plot that we might make, which is kind of this ternary version of the convex Hull plot. And what we show here is the dark spots are actually systems that are predicted to be thermodynamically stable, i.e. lying on this convex hull. And the spots that are colored by a particular color are off the convex hull. That means if you neglect any effects such as configurational entropy or other entropies or finite temperatures, generally speaking, these are going to be metastable phases. And further analyzing this, you can break it apart into different types of geometrical motifs. We find indeed that there's a wide variety of structures that could be metastable, including these cage-like species, ones where you have honeycomb type nets, chains, or sheets. And when we go into taking a look at those that we can calculate TC for, we restrict ourselves to metals, ones that have a high density of states at the Fermi level, higher symmetry systems. And one can compare, for example, the TC for just a phosphorus sulfide type of system at various pressures, and what would happen if you add a little bit of hydrogen to it. We can see that already adding just a single hydrogen to some of these systems boosts the TC by an order of magnitude. And the highest TC systems that we find, however, are based on these cage-like type systems, where a phosphorus atom has replaced one of the sulfurs within this cage. One can plot the electron localization function and see that this metallic structure is still somewhat intact throughout the 3D lattice, which is not what we find if we just put a single carbon atom into the system. When we put carbon into the system, we see that it actually really localizes these hydrogens and it breaks the metallicity of the structure. And in the case of phosphorus, that is not the case. And we see that the density of states at the Fermi level is almost a tiny bit higher than that of H3S. However, phosphorus is heavier than sulfur, so we expect the TC not to change so much from H3S, which is corroborated by different types of electron phonon coupling calculations. The ones in the brackets are using the Eliashberg formalism that is more appropriate for strongly coupled systems where the electron phonon coupling is larger than 1.5. So turning to some other ternaries, we might think about what would happen if you mix calcium H6 with H3S, since both of these binaries are predicted to have a nice high TC. And what we find via our calculations is that in most cases, the structures that emerge from the crystal structure prediction searches are actually not metals. They're insulators or semiconductors, and they can be understood in terms of calcium sulfide, which is a Ca2 plus S2 minus, so some sort of a ionic system with a gap, and hydrogen or H2 stuck into it in some ratio. So these aren't going to be promising for superconductivity. There was only one phase that emerged from our calculations as being either on the convex hull or close to the convex hull at high pressure, including the 0 point energy. And it actually remained as metastable down to lower pressures. So here I illustrate the phase. It is a CaSH3. Where we see here these types of honeycomb lattices that are made from sulfur hydrogen. So these would be HS type sheets that are separated by CaH2 type layers. So we have these separations. And if you calculate the density of states, we see that we're close to this kind of peak near the Fermi level. And actually, if you decrease the pressure, what ends up happening is you get some sort of bands crossing the Fermi level, so a bit of a Lifshitz transition, and because of that, you increase the density of states at the Fermi level, and you get closer to kind of a dynamic instability. So the electron phonon coupling increases, and the calculated TC or increases by about a factor of 2. So depending on what approximation you use, you might get up to TCs that are close to 100 Kelvin at about 125 gigapascals or so. But the idea is then that we could use this kind of a structure as a prototype where you can replace calciums by other electropositive divalent metal atoms and the sulfur with other selenium, tellurium, and so on type atoms. And so we've done this. We've carried out these sorts of, I guess, high throughput calculations that one would say, where you first just replace different atoms with each other, and then look to see if they are going to be dynamically stable as a function of pressure. And if they are, one can calculate the TC first using the crudest expression, the Alan Dines modified Macmillan expression using this value of mu star is 0.1. These are the TCs that we calculate, and the highest TC at the lowest pressure found with this Elias-Barak solution of the equations, it could be on the order of 120 Kelvin. We've also looked at the thermal stability of these phases just to make sure that they don't break apart, because when you're looking at metastable phases, you have to contend with the fact that they might have very low barriers for them breaking apart. And so molecular dynamics simulations have been performed, and here are some of the snapshots from the MD showing for this SRTE-H3 phase at 300 Kelvin and 40 GPa, suggesting that it could still be thermally stable at these types of conditions. Okay, we'll discuss this very briefly, and then I hope to talk a little bit about sodium. So another type of structure that has been found to be stable, as I mentioned before, this calcium H6 type cage was kind of a prototype that was stable in many of the different types of alkaline earth and rare earth metals. And these MH9 and MH10 type phases have been found too. But this MH6 phase is not stable for every divalent or trivalent metal atom, and we might want to understand why that is. So in order to try to interrogate that a little bit more, we turned to using the DFT chemical pressure analysis that has been pioneered by Danny Fredrickson's group, where one would calculate what the DFT energy is within a particular region of space, and so that would be called a voxel, and then expand and contract the cell somewhat, and then calculate the pressure in that way within that voxel, and then place this on top of project this, use some sort of spherical harmonics to interpret what this types of chemical pressure map might look like. And from that, you get these plots where the white denotes that you have a positive chemical pressure. So that means you would want to expand along that direction. And the black means you have a negative chemical pressure where you want to contract along that direction. So we have carried this out, for example, for calcium H6 versus strontium H6. And the calcium H6 is stable in this type of clathrate cage. The strontium H6 is not. It prefers to distort by making some of these contacts a little bit longer and some of them a little bit shorter, and in so doing, making sorts of one-dimensional helical hydrogen chains as opposed to these kind of three-dimensional hydrogen clathrate lattice. And you can already kind of guess that the size of the calcium versus strontium is important in these chemical pressure maps, and that's what we find. That around the calcium, we see this a black lobe telling us that the hydrogen cage would like to contract a little bit more around the calcium, but there is a balancing pressure, the white lobes up of the hydrogens pointing against each other, showing that this cage cannot contract more due to the repulsion between the hydrogen atoms. One can do a similar calculation for strontium H6 as well as for this distorted version. And what we see is an inverse of the chemical pressure map around the strontium, showing us that this strontium would prefer a larger cage. But it doesn't want to do that because now we have this kind of a black pressures, chemical pressures directed along the hydrogen atoms. And so what is preferred is this distortion, and the distortion it decreases the magnitudes of the chemical pressures, both between the hydrogen atoms and around the strontium atom. One can also do this to try to understand why certain ternary hydrides might be stabilized ternaries that are based upon binaries. The binary hydrides, like the lanthanum H10, can actually be viewed in terms of these, not only as in terms of the clathrates, but in terms of vertex sharing H4 tetrahedra and H8 cubes. And here's the chemical pressure map within it. If we remove this hydrogen atom from within this tetrahedron, one sees a really large black lobe pointing towards the interior of the tetrahedron. That's a negative chemical pressure. And we can help kind of satisfy this pressure by putting a boron atom within this cube, expanding it in such a way so as to contract the tetrahedron and therefore relieving this chemical pressure. And in fact, there have been a number of theoretical studies that have found that systems such as H8 are actually dynamically stable to lower pressures on the order of, say, 50 GPa than would lanthanum H10, and they are also superconducting. However, the TC is not quite as high as lanthanum H10. But this would be some way forward to maybe think about how we can make ternary hydrides that have some of these nice features for superconductivity based off of the binaries that we know. For the yttrium case, we find a bit of a different chemical pressure map because the yttrium is again going to have a different ionic size. It's much smaller. And in this case, what we find is that putting a carbon atom within this tetrahedron is actually going to compress the tetrahedra and expand the cubes. And the YC2H8 was found to be dynamically stable by us down to, say, 50 GPa with this expected TC. Okay, one can also use, all of these hydrides are going to break apart when the external pressure is removed because the barriers for breaking the hydrogen-hydrogen bonds are going to be quite low. So you could think about what would happen if you replace the hydrogens by some atoms that form much stronger bonds, potentially carbon or boron. And Roald here has done a lot of work with Tao Zhang Wolfgang and Davida and Tim Strobel, thinking about ways in which you could stabilize carbon-based clathrate cages by adding a little bit of boron into them and then filling them with small electropositive elements. And actually, then Tim with Li Zhu was able to predict and synthesize this strontium borocarbide type cage that actually really resembles this type of structural motif where you've taken the hydrogens now and replaced them with boron and with carbon atoms. And then we have a electropositive element in the center of the cage. And it was this structure was synthesized at about 60 GPa quenched atmospheric, and there are predictions of its TC. So we looked at borosilicides that were analogous to the boron carbides. In this case, we found that you would want rubidium or cesium within the cage for it to be dynamically stable. However, the superconducting critical temperature would be less than for the carbon-based systems because silicon is going to be heavier than carbon. Okay, so now going back to the boron carbides, what one can do again is this high throughput type of study, where now instead of just having a single element on the metal position, one can think about having at least two different metal elements. So we would do those types of calculations where we do the dynamic stability. Calculate the dynamic stability of the different species, and if they are dynamically stable, then we look into calculating the TC. And here we show the result. This is the TC, the stable species colored by their TC at 0 GPa. And what we find is if you have a trivalent metal atom, then this is going to be insulator or semiconductor. And the reason is the following. If the metal is trivalent, then the system becomes isoelectronic with diamond, and diamond has a gap. And so if you have a divalent or monovalent system, you're going to be hole doping it and moving the Fermi level down and getting some sort of a metallic system. And one can figure out that by varying the types of atom that you have in the metal atom identity and its oxidation state, you can hit different types of peaks in this system in the densities of states. And actually, one can correlate the average oxidation state with the TC because it's pretty much dependent on where this density of states hits. So the TC trends are that the highest TCs will be 1.5 plus average valence, which will be followed by the 2 plus average valence, and then these two types of combinations have about the same TC. And one can also estimate via this machine learning method that I mentioned earlier what the Vickers hardness is. And again, this correlates very well with the fact that the more metallic the systems are, the slightly lower the Vickers hardness is. So the highest TC we calculate is for this potassium lead type system that might have a TC of on the order of 88 Kelvin at 1 atmosphere. And then we have to think about stability. So first of all, we have done the phonon calculations, obviously the molecular dynamics types of calculations, and we find that this system is definitely going to be dynamically and thermally stable. Looking at thermodynamics, though, just straight up thermodynamics, if we looked at the formation enthalpy with respect to the elemental phases, it's not particularly favorable. But if we consider the fact that in principle, if there is no site preference for where the metal atoms lay, then you could have a configurational entropy term that is stabilizing the system. And under that assumption that configurational entropy would be important in these systems, and also considering the vibrational entropy terms, one would estimate that at high pressure and high temperature, you could have even a thermodynamic stabilization from the Gibbs free energy for this type of a system. But I must stress that this is just, we haven't done the convex hull calculations. That would take a lot more computational power than what we have done. Okay, I wanted to move, I'm not going to talk about this, even though I could. I wanted to move a little bit to this new study, just to give everyone some chance to ask questions. So now I'm going to switch gear and talk about different types of quantum behavior under high pressure by focusing on simple metallic systems. And so most of us here know that one other real advance done by Neil Ashcroft was thinking about what types of electronic structures would happen to so-called simple metals if you put them under sufficient pressure. And here is one of the studies that he and Jeff Neaton put forward, suggesting that if you compress sodium sufficiently high, that it should become an insulator, and the same for lithium. Because of the orthogonality of the valence electrons to the core electrons, and the interaction of the core electrons at such high pressures. And there has been actually a lot of experimental work done on sodium at these very high pressures. Here I show that you have some quite counterintuitive behavior. For example, as opposed, one would think naively that for most systems, the melting pressure should increase as you put pressure on the melting temperature. But in fact, for sodium, it initially decreases first and then afterwards increases. And here near the minimum of the melting point, you have quite a large structural diversity. Here are some of the interesting structures that have been shown. And what's more is that about 10 years later, after Neil's initial predictions here, there was experimental work showing that indeed at about 200 gigapascals, sodium becomes optically transparent and insulating. And crystal structure prediction searches done by Yaming Ma and collaborators found this sodium HP4 phase as being stable at these pressures, and there being a high degree of localization of the valence electrons in interstitial sites in this system, and which was also key for the fact that it becomes an insulator. So I'm going to talk a little bit more about this so-called sodium HP4, and this is a paper that's just out right now with Stefano, who's I think on this call right now. Okay, so here we show the sodium HP4 structure in a bit of a projection view, and these purple dots are the sodium atoms, and these little green dots are, well, one can calculate these are sites where you have non-nuclear attractors, but they're also sites where you have the buildup of the electron density localized in these states. And this is why the sodium HP4 would be considered an electride. Here you have kind of anions that would be centered around these positions that are electrons, and then you have the sodium plus cores as the cations. And when you do an analysis of this structure using your periodic codes to do projections of the density onto some sort of SP and D type states, the types of results that you get actually vary upon what kind of a radius that you use within which you do the projection. And because of that, what we have done is we turned to using the crystal program package, where we optimized a basis set for sodium. We optimized some of the exponents in the Gaussian basis to try to get a density of states profile that was matching up what you would get with plane wave codes, and also the minimizing the energy. And when one does a projection onto these atom-centered basis functions, what we find is that there is quite a lot of D character. There are two different types of sodium atoms, I should say, 1 and 2. And the projections on the two sodium atoms are slightly different. But in both cases, there's a large S to D type transfer, electronic transfer in this system, which was also noted by Neaton and Ashcroft in their paper in 2001 or whatnot that it was. Okay, so we've made this optimized basis that we call sodium right here. And we can calculate a number of different quantities with this basis, including the band gap, the density here at the non-nuclear attractor site, the Laplacian of the density, and the integrated charge. And we can compare it with what we would get using plane wave VASP calculations. And we see that indeed we get a quite good agreement between this atom-centered basis and what one would get with VASP. And then we start to think about, are there other ways that we could potentially describe this electron density? For example, by putting some sort of an S-type function right here. And that would be going along with some of the theories that have been proposed previously in thinking about these types of electrides, where you would have some sort of interstitial quasi-atom. So this was the work done by Mao Sheng and by Rold, and it was really quite pioneering work in thinking about the fact that you can actually have these electrons that go off the atoms and into these interstitial sites. So what if we would have some sort of an interstitial quasi-atom in the sense that you have a site without an electron, without a nucleus in the position, but you still have these types of orbitals, s orbitals, p orbitals, and d orbitals. So we can do that kind of an experiment by placing basis functions in these sites, and we have done that with S-type functions, by giving greater flexibility to these S-type functions by using more than one orbital exponent, and then taking away the P and the D functions from this sodium atom right here. So here we've done that for different types of variety of different types of ways. So here we just take the d orbitals away from the sodium. We find that it's metallic, so that's not a good description. We take away the d orbital, we put in an s orbital on the position of this non-nuclear attractor. Okay, so we're opening up a gap. So that's better. That's a good way to go. Again, we can put more basis functions in here with different orbital exponents, S-type. The gap is even more open, so that's again in better line with one would get from this optimized basis set and the plane wave codes. However, there are some discrepancies, for example, in particular in this Laplacian of the electron density. So it's not going to be a perfect match. And then there could be other things that are done, for example, by taking away both the p and the d orbitals. And again, you find in this case, you have a metallic system. In this case, the gap is too large. So here I show the electron localizations functions calculated using our optimized basis. And then the difference in the electron localization functions, for example, calculated using some of these other basis functions that I've mentioned. So just subtracting them on this grid. And we've considered that for this whole possibility, noting regions where the alpha is too small or regions where the alpha is too big in comparison to what we would get with the full basis set. So we think that this idea of that you definitely have this SP, this PD hybridization is really key for the formation of the electride state in these systems. And to study this a little bit further, we wanted to generate Wange functions for these valence occupied states. And so we have done this by in this formalism, we placed a basis function on actually the non-nuclear attractor site or the empty sphere. And then let this NMTO code does what it needs to do in order to generate a Vanier function that can describe this set of bands as best as it can. And here I show the actual full band structure with the downfolded band structure that one would get from this Vanier function. And we note that it does quite a lot look like this type of a blob around the non-nuclear attractor site, except that it has these tails on the 11 sodium atoms that are around this kind of cluster. And in considering this a bit further, we can see that if you take a hybrid orbital between this a PZ orbital and the DZ square orbital, where the axis would be pointing along the line joining the sodium atom to this to the center of this cluster, you get some sort of a hybrid like this. And if one were to put a number of PZ-DZ hybrids pointing towards the center of this lattice, then you get overlap between them that could be thought of in terms of multi-centered bonding between these PD hybrids. And so this is the interpretation that we would like to give for the formation of the electride state, that you actually have this S to PD transfer due to the Pauli exclusion and the orthogonality under pressure. And then one would have the overlap of these PD hybrids giving rise to this multi-centered bonding and forming this electride state. Okay, and now I've talked a lot, so I won't talk about anything more. I would just like to, highlight the people that have done this work. I would like to say that CDAC has sponsored really a lot of this work, and in particularly Katie Hillicky. She's done a tremendous amount of the work that I showed through the sponsorship of CDAC. Nisha Gang has done the work on the SPH and the carbon boron type systems. And Stefano on the sodium. And I would also like to thank my collaborators shown here. In many of them, Malcolm and Christian have been involved in the work on sodium, Li Zhu and Tim on the borocarbon cages, Danae also on sodium work, and Davida and Stefano Cortarolo in some work that I did not have a chance to discuss here, but on predicting super hard materials. Okay, and I would like to ask if there's any questions.
Well, thank you very much, Ava, for your wonderful talk. It's great to hear some of those details about how these calculations are actually done. Some of that detail is sometimes missing. If there are any questions, please raise your hand, or you can type your question in the chat. I have a question, Ava, about you alluded to a couple of times calculations at finite temperatures and building in entropy contributions. How does one do that? Is it just too difficult? And what would be the effects if you actually tried to do that?
Yeah, so typically we are assuming calculations at 0 Kelvin, obviously. And if we wanted to include the entropy corrections, the problem is that you need to do phonon calculations, and phonon calculations can be just very expensive. And so most of the time people neglect the entropy terms because of that. If you do just configurational entropy that's no problem. You can just, do analytical formulas typically. So that's not an issue. But if you want to include vibrational entropy terms, I think what's going to happen though is there are nowadays these machine learning interatomic potentials that have been developed. And they tend to be pretty robust for phonons. So with minimal training, I mean, you could do a training on some sort of a small MD calculation, and I think it's going to become more feasible to include these types of vibrational entropy contributions by potentially using machine learning to get the phonons and then to introduce these types of terms into the calculations. So I think that will become more often done.
Great, thank you very much. Roald has a question.
It's great to hear this work, Eva. On the superconductivity, especially in the hydrides, my external view is you guys can calculate it, but you don't understand the thing about it. That is, what I mean is if you get an optimum geometry, can you predict whether it'll be high superconductivity or low?
You mean without doing any TC calculation?
Without doing any calculations, yes, but just looking at the phonons.
Yep.
So is that a correct assessment of the situation? Tell me what I said that's wrong.
Okay. I think we can come to some trends with the hydrides. At least I feel like I can. So I can tell you that I think that if it's a three-dimensional hydrogen clathrate lattice, TC will be higher than if it's a two-dimensional clathrate hydrogen lattice, and it'll be higher than if it's a one-dimensional hydrogen, one-dimensional chain. And that if you have H2 units, typically the TC will be lower. So I think that there are some trends that one can see. I cannot tell you the number, but I can tell you that I have a feeling in my head of which one will be higher than lower. Just with the hydrides, okay, and with the clathrate hydrides. If I'm moving on to things like the sulfur H3 or phosphorus H2, in that case, I don't have enough of an intuition yet to be able to determine it. But I know that we want multi-centered bonding, just like in the phosphorus doped system with the SH3, the highest TC had a three-dimensional cage where the hydrogen was involved in the multi-centered bonding. And in situations where you had either lowered dimensionality or you didn't have as much multi-centered bonding, the TC was going to be lower. So those are kinds of the general trends that I see coming out of the data that I've seen. But of course, the closer you get to a structural instability. So if you have some soft phonon modes, typically TC will go up, though not always, because sometimes that also changes the omega ln part that goes into the calculations. So those would be the kinds of chemical trends.
Are the vibrations that contribute most to the phonon electron coupling, they are mostly in the hydrogen lattice, right? They're in the higher frequency vibrations. Is that right?
Yeah. So that's kind of interesting. I'll give you an example from the boron carbon cages. So in the boron carbon cages, what we found in some cases that the modes on first glance, the modes that contributed to TC are high, were low frequency modes. They were soft modes, and at first you would think, well, if it's low frequency, it's going to be because of the metal atom,
right?
But then when you actually look at the way that the atoms are moving, it was the boron carbon atoms. So if you don't look at the picture of the vibrations, you might think it's the metals, but if you look at it, it's the boron carbons. And what was interesting too in the boron carbon system, remember you have this clathrate cage where you have 4-membered rings and 6-membered rings. In all of the cases that we looked at, which was okay, maybe not everything, but in the cases we looked at, you had a distortion of that ring that was involved in the highest contributor to the TC. And so you could think of that in terms of, this distortion of cyclobutadiene or something like that is what you kind of start to think about. I haven't thought about it more deeply than that, except noted that it had to do oftentimes with the distortion of the 4-membered ring. And this was also something that Yaming Ma and John Say found for calcium H6, is that the distortion of that was giving rise to the highest TC in the calcium H6.
Okay.
Thank you.
But so in the hydrogens, it would be the hydrogen-based modes. Sometimes they are soft though, but you need to look at it.
Martin, go ahead, please.
Thanks. Hey again, Eva. It's
Hi.
really great stuff. Okay, I'll just ask this one because I was a bit perplexed on a technical note. So at some point you mentioned you're doing these studies of the metastable phases, and then the question is how metastable are they? And you claim you did. I haven't read this paper. It's probably explained in the paper. You did molecular dynamic simulations at 300 Kelvin. So, in your opinion, like, what are the caveats there? Because I assume there are a few. I'm not an expert in MD, but like you need to have a large cell enough to like allow a particular phase to decompose. You need to have potentially very long time scales.
Yes.
Also,
yes.
So,
So we have made supercells. I don't remember exactly which supercells we've made of which systems, but we have made supercells. And we have done it at various temperatures, at least the temperature where they are claimed to be superconducting. And then you do need to have longer time scales to make sure that you've probably sampled enough space for the decomposition. I can tell you, I don't have the paper written yet, but we have done MD simulations on a particular hydride type system. Other people have proposed it to be low pressure, higher temperature system, TC system, like maybe 3 GPa or 5 GPa. And we find that in that system, it's a ternary hydride. We find in that system that if you do MD, it like totally breaks apart. And so realistically, even though you have a dynamically stable system at that pressure, you need to actually go up to 50 GPa before the MD kills it. Like, so at 50 GPa, the MD won't make it decompose. So I hope to actually have time to write that one day.
Look forward to it. Okay, yeah, because most people never see anything decompose. So that's a good sign then. All right, thank you.
Thank you for that question, Martin. Sabri, please go ahead.
Okay. Hi, Eva. It's very nice talk. Thank you. I have a question. In some Venn diagrams of material, we have structures that only stable at finite temperature and dynamically unstable at 0 Kelvin. So when you deal with structure prediction in your code, how the judgment, like you find the competitive structure, you examine the dynamic stability, you find that it has a imaginary frequency. Then you say, okay, you like exclude these structures. How the judgment can be done in order to predict finite temperature structures?
Yeah, no, I get it. I get your point. Oftentimes you would get some sort of a you do your dynamic calculations and then you say, it's not dynamically stable, so let's forget about it. I mean, honestly, I think we have only considered structures to do finite temperature phonons on it if we have some experimental guidance to tell us that it should be stable. Otherwise, you might not do it. Again, I think that with some of the machine learning potentials, it's becoming more easier to do to develop them and then to do some sort of a MD. So that might become more standard. But I agree. Usually, you don't look at it unless you have some experiment that tells you should be.
Okay.
Mm-hmm.
All right, thank you, Sabri, for that question. Are there any further questions from the audience? Well, if not, then please everyone join me in thanking Eva once again for a really stimulating presentation on these really interesting new results. Oh, wait, Martin, go ahead, please.
I was only applauding.
Okay. Thank you so much. Again, it's been a real pleasure to see everybody here. Thank you so much.
Thank you very much, Eva.
Bye.